Hello students. So in today's session I'll be giving an idea about the pore pressure in soil for various conditions. So first let us discuss about the isotropic compression. So we know that the compressibility of soil, what is the expression for compressibility of soil? So here you can see the expression, that is the change in volume by the actual volume is equal to the volume compressibility multiplied by the change in effective stress. The negative sign indicates that as the effective stress is keeping on increasing, you are keeping on applying the effective stress, definitely there will be change in volume. That is why we are having a negative sign for this expression. Now this is a case of isotropic compression, that is the change in stress is applied equally from all the directions. So that is what is an isotropic compression. So what is the total change in volume of a soil element? So I know I already told you that soil comprises of the soil grains, the water, the air, etc. But here we are discussing about fully saturated condition. So definitely the change in volume may be due to the compression of the soil grains, compression of water, as well as the compression which is occurring due to the rearrangement of the soil skeleton. So in total it is delta Vg plus delta Vw plus delta Vsk, where delta Vg is the volume change due to the compression of the soil grains, and delta Vw due to the compression of water, and Vsk is due to the compression of the soil skeleton. So here in this table you can see the volume compressibility of the soil grain, water, as well as the soil skeleton. So we know that the volume compressibility is actually the inverse of the bulk modulus. Here you can see that in this table you can see the value of this compressibility is about 100 times that of water for the soil skeleton, and it is almost 1600 times the soil particles. Hence we can say that for most practical problems we need not consider the compressibility of water as well as the soil grain. We can only consider the compressibility of the soil skeleton. Now let us discuss about the pore pressure development due to the isotropic conditions. So let delta U be the increase in pore pressure due to an increase in effective stress. Sorry, it's not effective stress, total stress, delta sigma. There is just an increase in stress. Don't I'm not correlating with effective stress. Slight increase in stress of delta sigma is given, and you have an increase in pore pressure of delta U. And you have to correlate the delta U with delta sigma. So you are just using a factor called B. So you can equate delta U equal to B into delta sigma. B is obviously a pore pressure parameter. Now this soil is fully saturated. So we are considering it as a fully saturated condition. That means there is no drainage, so that water cannot flow, and there will be continuous increment of stress by delta sigma. Now let Cw be the compressibility of water and Cs be the compressibility of soil skeleton. So we had this expression already, delta V by V equal to minus Cs delta sigma dash, and this delta sigma dash obviously can write as delta sigma minus delta U. It is delta U. In this equation I haven't put delta U, but it is delta U. So delta V equal to minus Cs multiplied by, just take the V this side, so capital V into delta sigma minus delta U. Now similar to the change in volume expression for the soil, we have here a change in volume for the compressibility of water. So for compressibility of water, the element is the variation in the pore pressure. So here you have an expression delta Vw by Vw equal to minus Cw into delta U, where Cw is the coefficient of compressibility of water. Now this expression you just modify by putting the Vw to the right hand side. You have delta Vw equal to minus Vw delta U. Now this being a fully saturated soil, the porosity of the soil, it is volume of voids by total volume. So here the entire volume of voids is occupied by water. So the porosity is volume of water by volume of total volume of soil. So the volume of water you can replace as porosity multiplied by total volume of soil. So then we have this expression delta Vw is equal to minus Vw Nv delta U. That means we have converted the change in volume due to water in terms of the volume of soil. Now, as the soil is saturated and there is no drainage, and the soil grains are assumed as incompressible, then this total change in volume, initially what we had, will be equal to the delta VW. So you equate the change in volume of the soil grains with the change in volume of water, that is this expression, and you simplify this expression finally to get delta U into NCW plus CS, which is equal to CS into delta sigma. So now in terms of this just I am some rearrangement in the equation, we get delta U in terms of this, that is CS by NCW plus CS into delta sigma. Just some rearrangements in the equation, and again I am divide by CS in the numerator and denominator. You have this expression delta U equal to 1 by 1 plus NCW by CS delta sigma, and this term 1 divided by 1 plus NCW by CS is the pore pressure parameter for a completely isotropic compression case. Now that is B. So initially I have showed you this equation, that is delta U is equal to B into delta sigma, and that B we have found now, that is 1 by 1 plus NCW by CS. Now initially I told you that the compressibility of water is way too less compared to the compressibility of the soil skeleton, that is almost less than 0.01 times CS. So this CW by CS is practically 0. So for all cases in field, for saturated condition, that is if we do not permit the drainage, and the entire stress increment will be the increment due to the excess pore water pressure, because the B is 1 practically. So delta sigma is nothing but delta U. Now here you can see various values of B based on a study conducted by Black and Lee way back in 1973. That is, for various types of soil, varying from the soft soil to the very stiff soil, you have the various values of the CSK, that is the compressibility of the soil skeleton, and the equivalent value for the B. Now again here you can see for the degree of saturation how this B is varying. So as the degree of saturation is keeping on increasing, that is B definitely it is increasing and it is closing to 1. That means for fully saturated already I told that P is 1. So this keeps on increasing, and you can see how the variation takes place after 99%. It is almost, again it is not a steep increase. It is a flatter increase in the value of the pore pressure parameter. Now let us take a case of uniaxial compression. So in uniaxial compression you have the confinement, but the deviated stress is applied. That means you are applying, you have the confinement on all directions, but then again along with that you are having a change in stress only in one direction, that is only in the any one direction. Here I am just considering the vertical direction. So here you know that the effective stress in this particular direction is the applied change in stress minus the excess pore water pressure, but the other change in effective stress in the other directions, other two directions, it is only due to the change in the pore water pressure, because the change in stress I am giving only for the single direction. So this is actually a case of triaxial test where you are applying some deviated stress, but it is not completely triaxial test. Again I will explain again in the next after this. It will be the triaxial test, how what is the condition to find the pore pressure for triaxial test. Now the principal stress in this direction, that is here, which is the change in volume by the actual volume, that is equated as minus CS C1 into delta sigma 1 minus delta U, that is for this. And for the other directions you know that it is only the pore pressure, so it is CSE2 and CSE3 is the coefficient of expansion here, because due to this change in stress in this direction, the specimen will laterally expand in the this second and this third direction due to this compression. So in direction 1 you have the compressibility, and in the other directions, direction 2 and 3, you have the expansibility of the soil skeleton. So that is why this constant CSC1 is the compressibility of soil skeleton in one direction, and CSC2 and CSC3 or the soil expansibility in the other two directions. Now we will just equate that delta V by V. We have two different compressibility. One is for expansion and one is for compression. So compression, it is for the direction 1. So that is minus CS1 into delta sigma 1 minus delta U. This is for direction 1. And direction 2 and 3, it is CSC2 plus CSC3 multiplied by delta U. Now just take V to the other side and you have this expression delta V equal to V into this term. Then we know that delta VW by VW, that is the volume change in water, it is the compressibility of water multiplied by the pore water pressure, and that expression already we have modified like this in terms of total volume of soil, that is delta VW is equal to minus CW multiplied by N into V into delta U. So just equate for saturated soil, this change in volume due to water will be the overall change in the soil volume. So that you equate this expression with this was versus this, that you will get here. So that expression you can finally simplify as a constant equated as delta U by delta sigma 1, and this is the pore water pressure, the pore pressure parameter for uniaxial compression. So this again delta U by delta sigma, just rearranging this equation here, this equation, you take this delta sigma 1 this side, so it is delta U by delta sigma 1 equated as CSC1 divided by NCW plus CSC1 plus CSE2 plus CSE3. This is, this is for compression and this is for expansion. But if the soil is isotropic, that is, it has the same properties in all directions, and it is an elastic soil, definitely this the compression, the coefficient of compression as well as the coefficient of expansion will be the same as the compressibility of the soil. That is CSE1 as well as CSE2. All these will be equal to the compressibility of soil, volume compressibility of the soil, which is CS. So this we can simplify as CS by NCW plus CS. Again 3 CS, because this is CS and CS. So you have 3 CS here. Now what you do is divide with CS as in the previous case. So you have D is equal to delta U by delta sigma 1, which is equal to 1 by NCW by CS plus 3. That means this pore pressure parameter, this is the expression for a uniaxial compression case. So I already explained that in uniaxial compression you are applying the stress or increments in stress is in one direction and excess pore pressure will be in the other direction. Due to this stress increment, definitely there will be development of excess pore pressure that will be in the other directions. Now let us see a case of a triaxial test. So in a triaxial test, initially you are not applying any stress. So definitely the pore pressure is 0. That is excess. There is no excess pore pressure. Now in triaxial test, you have seen the video of triaxial test which I shared in previous session. So you know that initially you are applying some confinement. So due to that confinement, there is some generation of excess pore pressure delta UC. That is, let it be delta UC, because you are applying the confinement. And that confinement is delta sigma 3, that you know. Now you apply the deviated stress from the top. That is, if this is a specimen and you have applied confinement in all directions, now you are applying deviated stress in this direction. So here, due to the applied deviated stress, that is delta sigma D is the deviated stress. Applied deviated stress, you have a pore pressure increment. You just denote it as delta UD. And this excess this deviated stress is delta sigma 1 minus delta sigma 3. If you have seen that video, you will have this idea, this background. So you have the excess pore water pressure due to deviated stress as delta UD, and due to confinement you have delta UC. So the total this pore water pressure increment or the excess pore pressure is delta UC plus delta UD, and that you can denote as delta U. That is the total excess pore pressure due to the confinement as well as the deviated stress. So just depicting in terms of an equation, that is delta sigma 3 plus 0 is delta sigma 3. That is the horizontal stress which you apply. Now you have the vertical stress, which is the confinement plus the deviated stress. That is, finally you have this as delta sigma 1. That is, this is the increment in the major principal stress and this is the increment in the minor principal stress. Now the pore pressure is equal to delta UC plus delta UD, which is delta U. That is for the confinement case as well as for the deviator stress. So this is just a general idea of the test, that how the pore pressure is increasing in the triaxial test. Now here just a brief idea how this pore pressure I am explaining based on the elastic theory. So this is the change in volume by actual volume, which is expressed in terms of the volume compressibility multiplied by the stress. So here this I am as expressing in terms of bulk modulus. So already I explained that the volume compressibility of soil is the inverse of the bulk modulus, that is minus 1 by k, and you have the all the stresses multiplied by 3. So here, as it is a triaxial test, delta sigma 2 dash is equal to delta sigma 3. So just to modify this equation, delta v is equal to, you just take v to the other side, minus v into 1 by k and into this. And finally, some rearrangements. We need this in terms of delta sigma 1. So just make some rearrangements here. That is 2 delta sigma 3 plus delta sigma 1 by 3. You just write it as 3 delta sigma 3 plus delta sigma 1 minus delta sigma 3 divided by 3. Slight rearrangements in the equation. So delta v equal to minus v into this, you know, it is Cs. That is the Cs is the reciprocal of the bulk modulus. So minus v Cs into delta sigma 3 dash plus 1 by 3 into delta sigma 1 dash minus delta sigma 3 dash. Now this equation, you know that the change in volume of water is the volume compressibility of water multiplied by N into V into delta U. This is already the expression which we use for finding the pore pressure parameter. Now for a saturated condition, you know this delta V equal to delta VW. So equate both the equations, delta V and delta, this is delta V and this is delta VW. And you need this in terms of the delta U to find the constant. So you take all the terms related to delta U on this side. So you get this as simplified as delta U into NCW plus CS, which is equal to CS into delta sigma 3 plus 1 by 3 delta sigma 1 minus delta sigma 3. And further, in terms of delta U, it is delta U equal to, again we have this equation, that is 1 by 1 plus NCW by N by CS multiplied by delta sigma 3 plus 1 by 3 into delta sigma 1 minus delta sigma 3. This is B. Already we had this constant. Now let us see. So this is the pore pressure parameter for triaxial compression. So delta U is B into delta sigma 3 plus 1 by 3 into delta sigma 1 minus delta sigma 3. So you can bifurcate this into two. That is delta UC is equal to B into delta sigma 3 and delta UD is equal to B into 1 by 3 multiplied by delta sigma 1 minus delta sigma 3. That is, you have two pore pressure increments. One is due to the confinement and the second one is due to the deviator stress. But this pore pressure parameter is based on the elastic theory, but we know that the soil never behaves in an elastic manner. It is not an elastic material. So this equation, it cannot be generalized. We will have to make some modifications. So now how will you find the pore pressure parameter A? So you are generalizing the term with the pore pressure parameter B, but definitely for deviator stress there will be some difference in the pore pressure parameter, because initially you are applying the confinement and during the test the confinement is constant, because you have, for a particular confinement you are performing the test. So say you are applying a confinement of 40 kPa in all directions and then you are applying the deviator stress. So for the change in deviator stress there will be definitely a different pore pressure parameter. So let us consider that delta UD is equal to B into A. You have an additional pore pressure parameter. So this is actually you have found out earlier. So BA into delta sigma 1 minus delta sigma 3. And you simplify it as B into delta sigma 3. This is the total pore pressure increment or the excess pore pressure. So that delta you just incorporate this constant in that general equation. So you have delta U equal to B into delta sigma 3 plus A into delta sigma 1 minus delta sigma 3. So if the soil is fully saturated, we know that B is always 1. So delta U equal to delta sigma 3 plus A into delta sigma 1 and delta minus delta sigma 3. And in the triaxial test, you know that once you apply the confinement, it will be constant. There won't be any change in the confinement for a particular instance of the test, because you are only applying the deviator stress. So this delta sigma 3 term becomes 0. So you have delta U equal to A into delta sigma 1 minus delta sigma 3, or you can write it as A equal to delta U by delta sigma 1 minus delta sigma 3. So at any instant during the Traxel test, the core pressure parameter A is given by this particular expression, and this change in the deviator stress, that is delta sigma 1 minus delta sigma 3, is actually the applied deviator stress during the Traxel test. So now what is the pressure parameter AF? You know, it is correlated to the deviator stress. So AF is the value at failure. So it is of great importance, that is in field we need the value corresponding to the failure. So AF is given as delta UF by delta sigma 1 minus delta sigma 3 F. And this value of AF, it depends on the type of the soil as well as the stress history of the soil. So some typical values for the AF is given for various types of soils, as mostly clay soils. You can see here for the volume change, corresponding to the volume change, what is the AF value. So if it is an expansion due to shear, then you have the value ranging from minus 2.25 to plus 0.25. And if it is for a large contraction, then you have it from 0.75 to 1.5. And if it is expansion for heavily over consolidated soil, it is ranging from minus 0.5 to 0. So these are the various values which will help you to solve the field problems. So this is generalized value based on some experiences. Also, you can see the value of AF for over consolidation ratio. So you can see that the value of AF, failure AF, is decreasing with the increase in the over consolidation ratio. That is, if a soil is heavily over consolidated, definitely the AF value is less. And for normally consolidated soil, generally the value taken is 1. Value of AF is 1. Now let us discuss about the pore pressure parameter B bar, or the Skempton pore pressure parameter. So this excess pore pressure parameter, the excess pore pressure which is developed in the saturated soil. Saturated soil, especially for a soil with very less permeability. Definitely, relative this happens when the construction is rapid, and or if you are placing a load on the ground, or you are having some field construction like embankment. Definitely, there will be huge development of excess pore pressure, and this will result in the volume strain of the soil, and this will transfer the load on the soil skeleton. And this excess pore pressure development can be modeled by the finite difference method or the finite element method. Nowadays we are using the finite element as well as the finite difference methods, but there is a approach which was found way back, years back, by Skempton, that is using the pore pressure parameter B bar. That is, how will you find the excess pore pressure in the field. There are some based on some experiments he has arrived at a pore pressure parameter. So you have the pore pressure for a soil, and this pore pressure is actually this is the in situ pore pressure, and this delta U is the change in pore pressure due to some change in stress. That is, when you apply the load or when you are having a fill on top of the soil, definitely there will be change in the pore pressure. So this change in pore pressure already I have explained in the previous equation for triaxial test. This is the equation delta U equal to B into delta sigma 3 plus A into delta sigma 1 minus delta sigma 3. These are the Skempton's pore pressure parameters. So he found this way back in 1954. And you have this delta U as B into delta sigma 3 plus A into delta sigma 1 minus delta sigma 3, which is obtained from the triaxial test. So for field application, this delta U by delta sigma 1, you can take it as B bar. And this major principal stress, which is denoted here, which is the actual vertical total stress in the field. So this V bar is actually delta U by delta sigma V. So we are correlating the major principal stress with the actual vertical stress applied in the field. And this Skempton's parameters is always based on the total stresses. So we can see here all the equations in this equation as well. You can see it is delta sigma 3 and delta sigma 1. It is not delta sigma 1 dash or delta sigma 3 dash. That means the Skempton pore pressure parameters are always evaluated for the case of total stresses, not the effective stresses. So if you know the pore pressure parameter B bar, you can find the excess pore pressure developed in the foundations or in the field. Okay, and initial design values of B bar you can estimate based on laboratory tests or based on the field experiments, obviously. And during the construction, by the use of piezometers, you can actually measure the excess pore pressures. And if you find that this actual pore pressures are more than the predicted, you are predicting the pore pressure using the B bar. and you have the actual pore pressure in the field. And if you find that this actual pore pressure is considerably higher than the predicted pore pressure using this conventional method or using the previous experience by the application of B bar, then you can stop the construction such that you will wait for the dissipation of the excess pore pressure, and again you can start. So that way we can monitor the construction if you have this B bar. Now, for the field cases of slope stability in olden days, now we have the softwares, we have the finite element and all. But in olden days, you need some parameter to evaluate the pore pressure variation in slopes. So there is another parameter called the RU for the application in slopes. That is how the pore pressure is affected in the slopes. So we know that Bishop and Morgenstern developed the slope stability charts, and definitely they demanded that there must be a parameter for pore water pressure. So one such approach I am showing here, that is the approach in terms of the overburden stress. So that pore pressure parameter is denoted as RU, either small RU or capital RU. So this is actually the ratio of the pore pressure at a point to the total overburden stress. That is, here you can see RU equal to small u by sigma V. Sigma V is the overburden, or you can write sigma V as weight of soil into the height. So you can have RU equal to the pore pressure by gamma Z, where gamma Z is the overburden pressure. So in a field, if you given a slope like this, here this is the upstream and this is the downstream, you need to find the RU value for this downstream case. So you have the heights for various heights. You have this RU4, RU3, RU2, RU1. You have for a particular. You divide this entire slope into slices. So you have the slice A, slice B, slice C, slice D, and you have all these values. So you take the weighted average here for that particular slice. So that get it as H1 RU1 plus H2 RU2 plus H3 RU3 divided by H1 plus H2 plus H3. That is RU. You have RU for this slice. Similarly, you find the RU values for all the slices. That is for A, B, C, and D. Then finally, you take the average RU for this entire cross section as you have the area for this particular slice AA and multiply by the RUA. RUA you have already found for this particular slice. So add all the multiply AA into RUA. Similarly for AB into RUB, and for all the slices, and add all this, that is area into RUA. That you have to divide by the total area of the slice, that is AA plus AB plus AC plus AD, which will give you the total RU value for the particular cross section, which you can use to find the excess pore pressure in the case of slope stability. So this is just a crude method. Actually, this is an old method, but still effective, because in field the computation will be very fast. But actually, in nowadays we definitely rely on the various slope stability softwares. So need not go to such equations, but you have to have an idea that how these methods are developed, these old methods, because whatever new assumptions we are taking in the softwares, it is already based on these experimental data or these various correlations developed by various authors. So that is all about pore pressure. In next session, we'll be discussing about the deformation parameters of the geomaterials. Thank you.